Hello, seekers. Welcome to the fifth video of the blockchain series. So far, up until the previous videos, we went through the design, wherein we evolved a design to our solution to the cash recounting problem by introducing feature after feature in every step, and we tried to make that design foolproof, right? And through that design, we were able to eliminate many of the issues that we had. We were able to resolve the double spending problem. We were also able to resolve the scenario of a node trying to forge a transaction. In other words, if you see this transaction log or the transaction ledger between wherein there are two nodes that are participating, A and B. B can simply not take money from A's account. Such a transaction, what you see here, as B's account getting a credit of 2,000, it simply cannot happen without A's consent, right? We resolve that through our OTP kind of a solution. In blockchain terms, it is like a unique private key combination for every transaction. So it's simply not going to be possible just because B has the ledger of which has the account details or the wallet details of every possible account. It can simply not take money from anybody, right? The design simply doesn't allow that. What is, however, possible is for a transaction for a particular node to be able to give money and immediately come back and remove that transaction from the ledger. What I mean by that is a scenario of A printing a custom cash worth $2,000 or so. It gives it to B, and B broadcasts that, reprocesses that, which means that it would broadcast it to all the nodes. Once it does that, what if A comes back and knocks off that specific transaction from here? In fact, it cannot simply knock off a transaction because we learned that our design of our whole blockchain is immutable, right? Which means that you cannot go back and remove a particular transaction or edit a particular transaction. However, the only option that A has here is it can come back after giving $22,000 to B and B broadcasts that. A can come back and build a different block which doesn't have this transaction. That is something that A can do, technically, right? It's not going to tamper with an existing block, but it can go ahead and build an alternate block without this transaction. Now, would A be able to succeed with that? Not necessarily, because what A will also have to do is, it's not just going to be sufficient for A to build an alternate block without this particular transaction. A should also be able to build an entire chain of blocks after that without this transaction. Because remember, the fact that A gave $2,000 to B is already broadcasted to all the other nodes in the network, which means that everyone else would also be trying to build that blockchain with that transaction. So if A wants to build an alternate block without this specific transaction, it also has to build the subsequent blocks and chain them, and it can only succeed if A is able to build the longest chain without this transaction. Only then A will be the fact that that the A is trying to convey that this transaction never happened will be convinced in the network. In a sense, if there are three blocks, if the network has three nodes, A, B, and C, and if at all the player C tries to remove a particular transaction from this particular block, which is probably 3 blocks deep. Now the onus is on C to be able to build that alternate block here and also build the entire chain after this, which is at least 1 block longer than the chain in the network. Only then the other nodes in the network will consider this as the truth. Why? Because if you remember in our step 8 of the design, we evolved the design such that in the consensus framework, the network will consider whoever is having the longest chain as the truth. right? So in that sense, if somebody would want to, would want to build an alternate block and fake that they never gave that money, which means that they have to build that alternate block plus the entire chain that is at least one block longer than the rest of the network, and for it to be able to succeed. Now, in this, it might sound technically possible, but is it really feasible, right? Especially in a network where most of the nodes are honest, which means that, or in other words, when the compute power, when the majority of the compute power is controlled by nodes that are honest, in such a network, can a dishonest node will it be able to accomplish this? And that is precisely what we are going to derive and prove it mathematically, that such a possibility is negligible in a network where the majority of the nodes are honest, and they'll not, and when honest nodes control most of the compute power, the probability of a particular node being able to tamper with a ledger and build an alternate chain that is longer is very, very less, and this is negligible, and that is precisely what we are going to derive in this particular video. Now, you might have this question as to why we are talking about probability. Can we not be absolutely certain that a node in a network when the majority of the nodes are controlled by honest actors or honest nodes, can we not be absolutely certain that a dishonest node will not be able to build that chain, which is at least one block longer than the rest of the chain? Why should we talk about probability? Can we not be absolutely be certain in that situation? So I want to talk about one practical scenario, or how this whole the design of blockchain is going to manifest in the real world, especially a public a blockchain, wherein we enable peer-to-peer transactions between anybody to anybody in this world, right? So think about this scenario. So here I have 6 participating nodes or 6 smart piggy banks, and anybody should be able to make transactions with anybody, right? Now, while that is going to be possible through the design of blockchain, for a node to be able to seek consensus, it's not going to be practical for a node to seek consensus from every other node. There are going to be millions of nodes in that network, especially when you consider a public network. There are going to be millions and billions of nodes, and it's not going to be feasible for a specific node to, let's say this particular node comes back online, and we know that how will it find out the best possible, how will it sync up its blockchain? It has to look for the majority, or it has to look for the longest chain. In fact, it has to look for the longest chain, and it is not going to be feasible for it to validate that longest chain or look for the longest chain from the billion other nodes. How nodes are going to how this whole setup is going to manifest practically is there are possibly going to be clusters. When I say clusters, it is possibly going to be like there is going to be a cluster like this, and there is going to be a cluster like this, and within that cluster is what a node is going to look for consensus or seek consensus. So that is possibly how this whole design is going to work, on practical grounds. So which means that the idea of probability is inevitable, right? You're just not going to completely eliminate just because most of the nodes here are honest. We cannot be absolutely certain that a dishonest node will be able to build a longer chain. Because of this cluster, this specific node may not seek consensus from everything, but it is only going to seek consensus from this, and node here may not seek consensus from anybody here. It might only seek consensus from here, right? So that is the reason why we talk about probability, and we will derive we will derive the probability of a particular node that can actually, for a particular node that is dishonest, that can actually succeed in building this specific chain, which is one block longer than the majority, and we'll show that how that is that is going to be negligible. So in essence, what we are going to derive here is the probability. What is the probability that a dishonest node would succeed building the longest blockchain? And when we say the longest blockchain, it is a blockchain that is at least one block longer than the chain in the rest of the network, right? So this is the probability that we are going to derive. Now let's formalize this whole thing as a mathematical problem, right? So let's think of a blockchain in a network which has a rolling period of 5 years. So we discussed in one of the steps in the earlier videos where to optimize the space, we can consider blockchains that can go deep to a certain number of years, which means that we can go ahead and clear off the transactions before that. And the only caveat there is that every account that is participating in blockchain will have to make at least one transaction in that duration, right? So let's draw a blockchain. Let's model that blockchain. So let's say that you have a blockchain like this. So I'm going to keep it. Like this, right? So this is a blockchain, and let's take that this is the present moment, and this is 5 years. This is 5 years, right? In the past. So let's take, and this is a rolling window, right? So as we build more and more blocks, as we move into the future and we build more and more blocks, this pointer would we will keep dropping older blocks, and so that this one is always constant. The number of blocks is always constant in the chain. So let's consider this point. Let's break this thing into two parts. If you consider the oldest block to be 1, 2, and so on, and let's come until let's call this I, right? Let's consider this specific node. The significance of I will be very clear soon. So let's build this as I, and anything that is after that, let's start numbering it as 1, 2 up until Z, right? So your blockchain has two parts here. It has the total number of blocks is total number of blocks is I plus Z, right? So this is your total number of blocks in your blockchain. Now I want to see let's because we are trying to generalize this problem statement, right? We are trying to phrase this as a mathematical problem. So what I'm going to find now is, or what I'm going to state here is, let's introduce a variable called Wi. Now what does Wi refer to? Wi is the probability. Wi is the probability that a dishonest node succeeds in building a blockchain that succeeds in building a blockchain of length I plus Z plus 1. When it attempts to tamper with a transaction in the ith block. Okay. So let's talk about let's spend some time here and understand what this means. So we took a blockchain, which is a rolling blockchain, which has and we split that into two parts. It had the first part was I number of blocks, and the second part was Z. So the total number of blocks in that blockchain is is I plus Z. And we are defining a variable called Wi, which is nothing but the probability that a dishonest node can succeed in building that blockchain. It can succeed in building that longest blockchain, which is one more than the length of the existing blockchain, which is I plus Z plus 1. So this is the probability that a dishonest node can build a blockchain of length I plus Z plus 1. And let's call this as N, right? So N is equal to I plus Z plus 1. Let's use that variable here. And this dishonest node is trying to build this when it is trying to tamper with a transaction in the ith block, right? So that's how we are trying to generalize this whole problem statement, right? And it is probably trying to, it has given some money to another party, but the node that is trying to be dishonest has given money to another party, and that is present in this block. That entry is present in this block, and it is trying to get rid of that, which means that it is trying to build an alternate block at I and build a chain after that, right? So what is the probability of that succeeding is what we are denoting it by Wi, right? So given this, given this, so let's start deriving this probability, right? Now, how can we define? How can we quantify Wi? How can we quantify Wi? Right. Now, before we get started there, let's find the value of I can range from anywhere between 1 to Z, right? The value of I can range from 1 to Z. See that if the node is trying to, the dishonest node is trying to trying to revert a transaction that is very old, it is probably here. And if it is trying to revert a transaction that is fairly recent, it is probably here, right? So this value of I can range anywhere between 1 to Z. Now, given that, let us derive two values, W0 and Wn, right? Now, what is W0? Now, W0 is the probability that a dishonest node succeeds in building a blockchain of length I plus Z plus 1 when it attempts to tamper with a transaction in the zeroth block. Now, what do we mean by that? So, 0 is outside of this blockchain, right? So, we said that no, this blockchain is a rolling window, which means that it keeps moving, right? As new blocks get added, the old blocks goes away. So, W0 means that the transaction that started at the dishonest node that started at I has reached 0, which means that it has been overtaken by all the honest nodes, and they have succeeded building the blockchain for that network, right? Which means that the probability that if it is outside of this whole window, then there is no way that the dishonest node can catch up, right? So W0 is going to be 0. Same way, what is Wn? Wn is when the blockchain, the dishonest node has succeeded, is faster and is able to succeed building the next block, because remember N is equal to I plus Z plus 1, right? So the fact that your blockchain has reached, your dishonest node has reached the nth block means that it has succeeded, right? So which means that the probability that it has succeeded is 1, right? So let's keep this handy, and the value of W0 being 0 and the value of Wn being 1 will come in handy as we derive this specific value. So in the next video, we shall be actually deriving this value of Wi, and And then we will through that we'll be able to prove that how that probability is going to be negligible in a network which is mostly controlled by honest nodes. Thank you.
If you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.